we're going to be looking at forces and motion. So we're going to start bringing all the stuff we've done previously together, okay? So, there we go. Let's think about some questions. Why do we move forward when we walk, but our feet push backwards? That's an interesting thought, okay? And why is it, or how do objects move in space when there's no force acting on them? So if I could throw a tennis ball in space, it'll just keep going and going and going and going and going. But how does it do that when there's no forces acting on it? So these are important questions because we know forces act on objects, but what happens and why do we move the way we do? So we're going to bring it all together for us, okay? So we've seen our diagram, okay? So in previous lessons, we looked at the properties of forces, we've looked at the types of forces, we've definitely done how to represent them, we did components, and last time we did friction, okay, in a lot of detail. So now we're going to do force and motion, and we're going to break this down. So, important words for this time. Force, by now you can define force because we've done that lots. Net force. We have done net force. We didn't really define it. We did it last time, but it's when we take lots of forces together and we make it into one force. So net force, very, very important. We're going to look at Newton's first law of motion, and we're going to look at Newton's third law of motion. And I know it feels a bit funny because I skipped second law, but the first law and the third law go together. They actually work really nicely. So don't worry about the second law. We're going to get there. Okay, so don't worry. I haven't forgotten about it. So we're going to look at force and motion. Okay, just making sure we're all on the same page. There we go. Now, when we look at forces, we can get balanced forces. Balanced forces is something you have spoken about. What balanced forces means is that we have no net force. Net force is zero. Now, we've got to be careful. Net force does not mean there are no forces. It could mean that, but it doesn't necessarily. Net force is zero. What it means for us is that my object is either stationary, so not moving, okay, besides my hands moving, I'm stationary, okay, or it means that the object is moving at constant velocity, and it's the constant velocity part that's a little hard sometimes, because we go, well, if the net force is zero, how's it still moving? I'm going to show you. Okay, so don't stress about that. I really am going to show you. So balanced means that the forces acting on the object cancel each other out. The object's stationary, or it's going at constant velocity. Okay? Oops, there we go. So we also get unbalanced forces. Now, we don't use unbalanced forces when we describe things. I'm using this just to get us to a point. Okay, so just hang with me, okay? What that means for us here is that the net force is not equal to zero. I've specifically said not equal to zero, not bigger than zero or smaller than zero, because remember, forces can be negative. The negative gives me direction. So I'm not telling you here for them to be unbalanced that the force has to be bigger than zero or it has to be smaller than zero, because I'm not indicating direction, okay? But it has to have a value, What it does mean is my object's accelerating. Now here we've got to be careful with our terms, because we use the word decelerating in everyday language. So we'll say, if we're driving in a car, the car decelerated till it stopped. And we understand that to mean that it got slower. In science, we don't use the word decelerating because it's a language thing. It's not a science word, okay? So in science, we would rather say we have a positive acceleration, which means my object's getting faster, or we say it has a negative acceleration, which means it's getting slower. And when we get to Newton's second law, we're going to talk about the direction, okay? So by accelerating, what I mean is that the object's velocity is changing. Okay, that's what we mean. It's not constant. All right. So we're also going to look at force pairs today. That's Newton's third law. Now, this one becomes interesting because up till now, we've looked at forces acting on a single object. Force pairs are when we have two objects. So we're looking at the objects that are in contact with each other, okay, or the objects that are creating the forces. So force pairs becomes important. This whole section here that we're doing today, these are explanation questions. There's no calculations. This is explanation. This is where you have to write it down. So we've got to make sure that we're using the correct language, okay? So, what have we done so far? We've looked at force and motion. In the next, we're going to take a short break, and then we're going to look at it in a lot of detail. Okay, so I'll see you in a couple of minutes. Welcome back. Now, so we've spoken a little bit about the theory. Now we're going to look at how it works, because it's really important that we understand this. So again, we're still looking at forces and motion, okay? There we go. We're still looking at forces and motion, and what we're going to do now is we're going to talk about this. What happens when the net forces acting on an object are balanced? In other words, my net force is 0. Okay, so we're going to go to a quick animation. So here we have our trusty men, which we've seen before. And remember, the size of the men represents the size of the force. We have our little crate. What we're going to do is we're going to put the speed on there. So you need to keep an eye on the speed. And we're going to put the values of the forces as well, and I'm going to put the sum of the forces. So we're going to keep track of all the stuff that's happening, all right? So I want you to pay attention to the speedometer, look at what it's doing, and look at what the sum of the forces are, okay? Because this is very important. So we're going to put a little man on the side. He's got a force of 50, and we're going to let him go. Well, obviously, if I pause it, the left force is bigger, so there's a net force, and it's moving to the left. It has a speed. Now, if I just let this go, he's going to get faster and faster and faster and faster, and eventually he'll stop on the side because there's a little thingy on the side that stops him. What happens now if I put another man on this side? If we look at it, he's now pulling to the right. The net force is 0. Our gut instinct here is, while the forces cancel out, the object's going to stop, but it's not. Watch. That speed stays constant. And now we're going to have to reset because I've got to the end of that. So we'll reset this again, okay? So we'll put the man on. He went for a little bit. Okay, let's just make sure we've got the speed there. Okay, so you were starting to speed up. I put the other one on. Net force is now 0. If you look at the speed, it doesn't change. It's going at constant velocity. This is so, so important. My sum of the forces is 0 because we have equal amounts on both sides and they're pulling in opposite directions. My object goes at constant velocity. Now, in this simulation, the object eventually stops because we've got a little thing there to stop it, okay? But if we could have an unlimited length of grass that they're on, shall we say, they would just carry on forever and ever and ever and ever because the forces are balanced. So it will just keep moving. If we reset this again, And this time, I'm going to put the two forces on straight away. We have equal forces. Now watch. It doesn't go anywhere. It stays stationary. This time it stays stationary because it was stationary originally. So what happens when we balance forces is that whatever motion the object had, it will continue with that. So if it was stationary, like we've got now, it stays stationary. If it was moving and we balance out the forces, it'll keep moving at constant velocity, okay? Or constant speed. We say constant velocity because it's not going to change direction. For an object to change direction, we have to change the force acting on the object. So the net force isn't zero anymore, okay? Because the forces are vectors. They have size and direction. So when we balance forces, and I'm saying it a lot because it's important, if the sum of the forces is zero, my object will stay stationary, or it'll move at constant velocity. Okay, so now watch. I'm going to add one here, so now we unbalance the forces. It starts moving. As soon as I add another one there, constant velocity. Okay? Now I keep adding to the right, to the left, just because it's closer to me. What happens if we do it to the right? I need you to see that it actually makes no difference. So we start there. Okay. He's not moving. Let's add to the right first. So now starts to move a little bit, and I add one there. Now it's going to go to the right, because that's the motion it was in when I balanced out the forces. Okay, that's very important. So it keeps going in whatever direction it was going in. We good? All right, so we know net force, when it's zero, an object will either stay stationary or it's going to keep going at constant velocity in the direction it was going in. Very, very important. Now, what happens when, well, let's summarize it first. Balanced forces mean net force is zero. It also means the object can be stationary or it's moving at constant velocity. No acceleration. Acceleration is zero. I'm making a big emphasis out of this because it's something that gets implied in a question. So they'll tell you that an object has got constant velocity. You need to know that that means acceleration is zero. So they won't tell you that. It's implied, okay? That gets us to Newton's first law. Your laws are very important. You have to know them by heart. They are very strict with this. So, it says to us, a body will remain at rest. Where are the important words? So we need to make sure we've got those. In its state of rest, or motion at constant velocity, unless a non-zero resultant or net force acts on it. Here, I'm not using the words balanced or unbalanced, okay? They don't like those. Non-resultant, non-zero resultant means the F net is not zero, it's bigger. You can use resultant or net force. Those two are the same. You don't have to put both. But what am I telling you? For Newton's first law, an object tends to keep going in the direction it's going in unless the forces around it change. Very important. So that's Newton's first law. This comes up in explanation type questions, which we're going to see a little bit later. Very important. This is your easy marks in an exam. These are your giveaway marks, okay? Now, what happens when the forces aren't balanced? Okay, so we're going to go back to our men, because I really like them. Okay, so here we go. Let's reset it. Okay. Let's start with them balanced. And I've done this a couple of times. There we go. They balanced. Ain't going to go anywhere. They balanced. They're happy. If I unbalance them, so I'm going to add one here, we can see, and watch the speedometer, It's getting faster and faster and faster and faster, okay? Because we have 100 newtons to the right. Now it stops here because, well, we got to the end of there's a little block to stop it, okay? But we had a net force to the right. It was unbalanced, and it accelerated to the right. It went in the same direction of the bigger force. That makes sense to us. It's not going to go in the opposite direction of the bigger force. Or will it? Okay, so watch. Now what we're going to do is let's do this. So now I'm going to start with it going to the left. Okay, I haven't started it yet. So now he speeds up, and we can see, but the red team don't want to lose. So I'm going to put one. What's happening? The speed's getting slower. So as soon as I put on the one to the right, it's still moving to the left because that was its motion, but now it's slowing down. It's experiencing a negative acceleration. But my net force is to the right. So watch what's going to happen. It's going to slow down. It stops for a brief second. And now watch. Now it's going to speed up in the other direction. Okay? Now it's a tug of war. So let's just pause it there. It's speeding up. It's getting faster. Let's add someone over there. Okay, so now I've added to the left. So we knew it was accelerating to the right because that's where the net force was. Now I've made it so the net force is to the left. Watch. It's going to go slower and slower and slower while it's going to the left and then change direction and go to the right. So as soon as we have a net force, the acceleration that it experiences is always in the direction of the net force. Notice I'm not using deceleration, okay? That acceleration can mean that either it's going to speed up, like we saw in the beginning, or it's going to slow down and then change direction if we keep it in that direction. So my acceleration and net force are always in the same direction. They're both vectors. So they both have size, they both have direction. So we've got to keep that in our mind when we do this. So let's go back to our summary, okay? F net not equal to 0. I've not put it as a positive or negative because that's a direction thing. And also, when I did the simulation with you, I didn't say to the right was positive and I didn't say to the left is positive. Those are decisions we make later on, okay? So the point is that it's not equal to 0. The object will accelerate, not accelerated. The object will accelerate. Remember, by accelerate, I mean the velocity will change. Either it's going to get faster or it's going to get slower. That's what acceleration means. Velocity changes. Forces can be balanced or unbalanced when acting on the same object. They have to be the same object. I can't talk about balanced forces if they're on two different objects. That's what we're getting to now. Same object, okay? Now, what happens when we talk about different objects? So this is quite an important question. Why is it that when you push down with your foot, when you're walking, you go forward? Because if we think about it, we're actually pushing backwards, but we're moving forwards. How does that work? Well, let's talk about it. So we have a foot pushing down. The foot pushes down on the floor. And in fact, your foot pushes a little bit backwards. But as a consequence of your foot pushing downwards, okay, the floor pushes back on you. So what's actually happening, and let's just take these ones out, and I'll show you from here. So you get it in different steps. So over here, you pushing down. So this is the force of your foot on the ground. At the same time, the ground pushes up on you. So this is the force of the ground on your foot. This force is the one that makes you go forward. This is known as a reaction force. This was quite a breakthrough when Newton came up with this, because it explains a lot of things for us, because no one had thought of it before. But the fact that we get these reaction forces is very important. So your foot pushes down, and because the ground is pushing back at you, it makes you go forward. Could you imagine how we would walk if we pushed down and we didn't go forward? Think about if you walk on sand. It's harder because the sand, it still pushes back at you, but because the sand is soft and it all sort of like goes all funny underneath your foot, it's more difficult. Okay? So sometimes athletes will run on a beach to make themselves stronger because it takes more muscles, all right? I don't like walking on the beach for that exact reason. But we push down, ground pushes back at us. It happens everywhere. If I take my hand and I push with my other hand, both hands are actually pushing on each other. Even if I don't think this hand's doing anything, it really is, because they're in contact. When we look at the earth, I'm attracted to the earth, and I move towards the earth if I jump up, but the earth is attracted to me as well. The only reason why the earth doesn't move is because it's so big, and the force I'm exerting on the earth is so small that the earth goes, I'm not moving, I'm big, you can come to me. So I go to the earth because I'm smaller, it's easier for me to move, okay? That gets us to what we call action-reaction pairs. Okay, they like these are known as force pairs. First of all, this is the important thing. They act on two different objects. They do not balance each other. This is very important. Balanced forces act on the same object, but because we've got two different objects, they can't balance each other out, even though they are exactly the same size. They are equal in size, but they are opposite in direction. Together, this gets us Newton's third law, which says to us, when object A acts on object B, or exerts a force on object B, simultaneously, in other words, at the same time, they exert an oppositely directed force of equal magnitude on object A. So if object A exerts a force on object B exerts a force on object A of the same size, but in the opposite direction. Please be careful here. You may not say for every action there's an equal and opposite reaction. Okay? It's not accepted. It has to be this because it's about forces. And we're going to do, and this is definitely explanation only. Okay? That brings us to the end of the theory part. We're going to take a short break, and then we're going to do some questions. So I'll see you in a bit. Welcome back. Now, we've done lots of theory. We've done Newton's first law, we've done Newton's third law. Now we need to get into the nitty-gritty. What are the questions? What are they going to ask you so that they know you understand these concepts? Okay, because that's important. So, first question. Explain. The word explain means that you can't just say balanced or unbalanced. It means you've got to describe for me what's happening. You've got to show that you understand the science, okay? So explain means we'll need sentences. Very important. If they had just said state, then we can say balanced, unbalanced. But they didn't. They said explain. So I've got to describe what's going on. Explain whether the following objects experience balanced or unbalanced forces. First question, a car accelerates down a slope. Keyword, accelerates. Accelerates means velocity isn't constant. If velocity isn't constant, then the forces are unbalanced, okay? So, explain, well, velocity isn't constant. There we go. Therefore, unbalanced forces, okay? So basically what it means for us is that when I ask you to explain, you've got to give me a reason for your answer, okay? This would be worth 2 marks. 1 for being able to know that they're unbalanced, and then 1 for telling me why they're unbalanced, okay? Next one. A moving truck where the brakes are applied. So it's moving, and now we're applying the brakes. So now they're going, do you understand what it means when we apply the brakes? The point of applying brakes on a truck or a car is to stop it. So in other words, we're wanting to change the velocity. If the velocity is changing, then the forces must be unbalanced. Okay, so it's about reading the question. So again, we would say the velocity is changing. Therefore, it's unbalanced. Straightforward. A rocket that leaves the Earth's surface, and it's leaving the Earth's surface. Now we've got an interesting question, because I'm not telling you anything about the motion of the rocket. This becomes a little bit of a gray area, because we could leave the Earth's surface at constant velocity, and it would be very difficult and take a very long time. But with rockets, they will absolutely be accelerating. So this one's a little bit of a gray area question, and exams, they're definitely more specific. But I've put it in here deliberately so we can talk through what could possibly be happening. If the rocket is going at constant velocity, then the forces on it would be balanced. It can still leave the Earth's surface because it has a constant velocity away from the Earth. It will eventually go away. But more than likely, it's going to be accelerating because that's what we want. Otherwise, it takes too long. And remember, it's got to overcome gravity, and it's going to be heavy, so there's got to be big forces acting on it. That means the forces on the rocket probably will be unbalanced. Why? Because it's got to accelerate. Its velocity's got to change. Okay, so I'm not going to state whether it's either. It depends on the situation, so I'm not going to write anything down for this one. If it's going at constant velocity, the forces are balanced. If it's accelerating, then the forces aren't balanced. It all depends on the situation, okay? Next one, a bicycle that is traveling at constant speed of 35 kilometers per hour. First of all, that's ridiculously fast for a bicycle, but that's all right. I've used the word constant speed now. That's okay. Don't worry about it. I know speed's a scalar, so we don't worry about direction. Velocity is a vector, so I need direction. That doesn't matter. The point is that it's got a constant value. its velocity or speed isn't changing. That tells me that the forces must be balanced. The speed is constant. It's not changing. Balanced forces, okay? So this means that, okay, we won't put it as velocity. We'll say the speed is constant. All right. Therefore, balanced forces. Constant speed, balanced forces. We're happy with that. Okay, next one. Now, a brick rests on the floor. Rests means it's stationary. It's implied. Okay, they're not telling you it's stationary, it's implied. A horizontal force is exerted on the brick to the right. Friction cannot be ignored. Important words. I'm not giving you the value of the horizontal force because that's not actually what we're looking for here. I'm just telling you that we have a brick on the floor, it's resting on the floor, and I'm pushing the brick, but it's not going anywhere, okay? First thing I want is I want a force diagram and a free body diagram showing the brick at rest. Remember, force diagram means the brick has to be a box. So let's do the box. So this is the first one. We have our box. The brick is being pushed to the right. So that's the applied force. At the same time, friction can't be ignored, so friction is going to act in this direction. What's important here? What am I looking for? Those two lines must be the same size because the brick is at rest, which means they're balancing each other out. But we're not finished. Be careful here. This question would be worth 4 marks in an exam because there's 4 forces. Remember, we still have gravity which acts down and the normal force which acts up. Remember, with a force diagram, the forces must be drawn exactly as they act on the object. So the normal force from the surface upwards, gravity from the center. It was a pushing force, so I push it towards the brick, and friction between the surface and the brick. Now they want the free body diagram. So if we go to the free body diagram, remember that's a dot. These ones are easier. FG, Fn. Now my applied force goes to the right and friction goes to the left. What am I looking for when I do this? You don't have to use a ruler, but visually, the applied force and friction must be the same size. The gravity and the normal force must be the same size. Here, I've drawn them, all 4 of them, relatively the same size. I don't actually know if they will be, because I don't know the mass of the brick. That doesn't matter, okay? But it's so that the 2 horizontal forces are the same size, the 2 vertical forces are the same size, okay? Ooh, now same brick. Now it's going at a constant velocity to the right, and they want the same diagrams. Now we've got to be careful, because we're going to be very tempted at this point to go, well, it's moving to the right, so the force to the right must be bigger. No. Keywords: constant velocity. Constant velocity means balanced forces. Be careful. It's a trick. It's to make sure you're reading properly and you're understanding what we're asking you. So the force diagram, okay, let's do the forces in a different colors so it makes it a bit easier for you to see. We still have the applied force. We still have friction. We still have gravity. And we still have the normal force. In fact, it's exactly the same diagram we just drew, where the applied force and friction are the same size, Gravity and the normal force, same size. Let's do the free body diagram. Okay, free body diagram. There we go. Gravity, normal force, applied force, and friction. What are we looking for? Same as the last one. The horizontal forces are the same size, and the normal force and the gravity is the same size. Okay, and it's a visual thing, and so that when I look at it, I can see they're the same. We're not going to take a ruler and measure them, because they're not accurate diagrams. It just needs to look like they're the same size, and we'll be happy. Okay? Next one. Now they say to me, it accelerates to the right. Change in velocity. And it's change in velocity to the right, which is actually this side for me. Because it's going to the right, that means the force that's being applied is bigger. Remember, friction doesn't have to always match the applied force. We've done static and kinetic friction. So what we're looking for here is this. We still have our box. Gravity and the normal force are still the same size. I haven't changed the mass of the brick. The brick's also not moving vertically. So those forces are balancing each other out, okay? This is the difference. I have a big applied force, and the friction must be smaller. Now I'm wanting to see that you understand that the force that's pushing it to the right is bigger than the friction which is going to the left. They are unbalanced, so it can accelerate to the right now. When we draw our free body diagram, we have our dot. Fg goes down, Fn comes up. Now's the big difference, okay? F and friction. I've made it very obvious that the force to the right is bigger than friction. Here, that's what I'm looking for. I didn't tell you how much bigger it was. I didn't tell you how big the acceleration is. That's not what I'm worried about. So I'm not worried if in real terms it's exactly correct in terms of how much bigger or smaller the two forces are. I just want to know that you understand that the force to the right, which causes the acceleration, is bigger than the force to the left. But at the same time, the normal force and the gravitational forces are still equal. Okay. All right. Next one. They love questions like this. There's a big emphasis in the curriculum about road safety. Explain why. Explain again. It is important to wear a seatbelt when traveling in a car or a bus or any of those things. Why do we need to wear seatbelts? This is about Newton's first law. Completely about Newton's first law. Remember, when you're sitting in a car, you're traveling in a certain motion. The forces may or may not be balanced. It depends on whether you're accelerating. When the car stops suddenly, your body will want to keep going forward. Why? Because now the forces on it are balanced for a while. We haven't quite, the force of the brakes doesn't get to us straight away. So what happens to us? We keep going forward. Remember, it's also to do with a term called inertia, which is related to Newton's first law. Everybody has inertia. That's why it's hard to get going, okay, or hard to stop. But we keep going forward, and because we keep going forward, we need something to stop us, okay? So what does the seatbelt do? The seatbelt pulls us backwards. It's also why we have airbags. So Newton's first law says to us, keep going forward, no resultant force on us. Seatbelt gives us a resultant force that pulls us backwards. Very important. Okay, they like questions like this, by the way. All right. So, here's our summary. When the net force on an object is zero, the forces are balanced, and the object will either be stationary or move at constant velocity. When a force is exerted, and together this is Newton's first law, okay, just so we know. When a force is exerted on object A by object B, then object B will exert a force equal in magnitude, but opposite in direction on object A. That is Newton's third law. That's just another way of writing it. Two very, very, very important laws. And that gets us to the end of this lesson. Next time we're going to look at Newton's second law, so I'll see you then.